All right, everybody, welcome back. Um, in the sort of commercial break, I noticed a typo at the end of this slide here. And I know that I said that the surface integral of f along a surface measures the rate at which, say, if that vector field f is modeling some fluid flow, it would measure the rate at which that fluid is flowing through the surface S. I think I misspelled that before and wrote though, which makes no sense. Okay, so we fixed that one up. But enough about words and splitting hairs about that. Let's do a very nice and encompassing and possibly difficult and long-winded example of a surface integral of a vector field over a surface that has two pieces. So we can kind of see what one of those looks like too. So let's let E be the solid region of space that is enclosed between the paraboloid y equals to x squared plus z squared and the plane y equals to 1. And let's let S be the boundary surface of this region. So this three-dimensional region is what's inside of here. Okay, so notice this is a closed surface, and the inside is here, the outside is everything out here, okay? And so this surface has inherently two pieces. This paraboloid opening in the y direction, that's one piece, and then this planar piece, or just really, this is like a disk, modulo the fact that my drawing's a little funny. This is supposed to be a disk. So we'll call S sub 1 the paraboloid piece. And if you look, say, stand along the y-axis and stare back at the xz plane, what you'll see, the sort of projection of that paraboloid piece is just the unit disk. If we're stopping at y equals 1, this is height or radius 1. So we will get the unit disk in the xz plane. So we're graphing that paraboloid. Y is a function of x and z, where x and z vary over the unit disk in the xz plane. Okay, and then similarly, the second region, S2, is literally just the graph of the function y equals 1 restricted to the unit disk in the xz plane. So we can really think of this as the unit disk given by x squared plus z squared is less than or equal to 1 in the plane y equals to 1. Okay, so two ways to kind of think about that one. Okay, so we're going to ultimately do a surface integral of a vector field over this total surface S. But in order to do that, we'll have to break it into two pieces and do an integral over S1 and an integral over S2 and add those two together. So that means that we're going to need to do separate parameterizations for S1 and S2 and separate considerations of how to get those outward pointing normal vector fields for each one of those pieces. So let's start with S1. Notice that it is the graph of a two-variable function where y is the dependent variable and x and z are the independent variables. But that's fine. It's still a graph that way. So if we let h of xz be x squared plus z squared, then y equals to h of xz, that graph is that piece S1 as long as we restrict to xz over the unit disk in the xy plane. So we could choose to parameterize it with that graph of a function sort of trick that we learned back in the first video of today's lectures. So we'll let x and z stand on their own. X is for x and z is for z. And then y is x squared plus z squared, the function at hand, where the pairs, again, vary over the unit disk in the xz plane. Now, I know what you're thinking because we've already done something like this before and then changed after we made this consideration. So you might notice that since that region, that unit disk in the xz plane, is much more nicely described by polar coordinates, you could just as well choose that x is u cosine v and z is u sine v, and then the parameterization becomes r of uv is u cosine v in the first component use sine v in the last one, just replacing those with polar coordinates, and then the middle guy, x squared plus z squared, becomes just u squared. Right? So this is very similar to that example with the cone that we saw earlier. And then it would be easier to do your integral maybe at the end, because u varies between 0 and 1, or sorry, yeah, u varies between 0 and 1, and v varies between 0 and 2 pi. So you might like to do it that way. But I know that we've already kind of done a surface integral today where we did make that sort of change to our parametrization. So I would like to showcase to you today how it might work if you chose this original choice instead. And I think there's actually something coming up in a minute that's going to make this original choice here a little bit easier to work with. So we're going to go with this one instead. So for today, we'll have R1 of xz equals to x in the first component, x squared plus z squared in the second component, and z in the third. And here the 1 decorating the R stands for the fact that we are parametrizing S1. That's just a decorative choice that I made because I know we're going to be doing this 2 different times, and I'd like to distinguish between the 2. Okay, so we'll go with this parametrization. So now that we've got that, let's compute those tangent vectors. One will be done with respect to x now, and the second will be done with respect to z. Already I'm liking this choice that I made because these tangent vectors are easy to compute, right? The derivative of x with respect to x is 1. The derivative of x squared plus z squared with respect to x is 2x. And the derivative of z with respect to x is 0. And likewise, the derivative of x with respect to z is 0. The derivative of x squared plus z squared with respect to z is 2z. And the derivative of z with respect to z is 1. So I've got my 2 canonical tangent vectors on this surface that have been handed to me by this choice of parametrization, R. So the cross product of those should then look as follows. In the first component, we'll have 2x. In the second component, we'll have minus 1. And in the third component, we'll have 2z. Okay. So then to determine if this cross product points inward or outward from the surface S, let's pick some values of x and y and see what's the corresponding point on that surface. And then maybe let's draw these vectors and see if this guy points inward or outward. So I'm going to pick x equals 0 and x equals 0 and z equals 0. That'll be right at the sort of like bottom, essentially, of that paraboloid. So when x is 0 and z is 0, the corresponding point on that paraboloid is the origin, 0, 0, 0. Right? That's probably a better way to say it. So we can use the formulas we had for R1x and R1z, those tangent vectors, and get that the x1 was 1, 0, 0, and the z1 is 0, 0, 1. Oh, hey, I know those vectors. Love them, right? So let's put those down here, and let's see. Which one's outward pointing? Well, to be outward pointing from this surface over here, you'd be pointing that way, right, in the negative y direction. And if you do the right-hand rule, or if you just look at the formula that you have for this cross product you've already computed, you'll see that it is, in fact, the cross product Rx cross Rz that is pointing outward from S along this first part, S sub 1. Okay, good. And okay, so we've drawn that here. Good. So now that we've got that, we'll kind of set that work off to the side so that we can come back to it later. Let's take care of this awkward, difficult part for the second part of the surface, S sub 2 now. This is the unit disk in the plane y equals to 1. Well, this is really just the graph of the function y equals to 1. That's technically a function of x and z. It's just not a very interesting function of x and z. So we can do it the same way, where we let x be x, z be z, and y be 1, where again, the pairs x and z will vary over the unit disk in the xz plane, because that's what you see when you project that to the xz plane. Okay. And again, if you were so sort of curious about this, you could have also chosen to model everything with polar instead, because you know that if you're going to be working over the unit disk in the xz plane, polar coordinates might be the appropriate choice to be making. So this would be that description in that case. But again, I'm going to prefer this first one because it's actually just a little bit easier to sort out what are those outward pointing vectors. Like in S1, it was very easy to do that because the tangent vectors that we had at hand were so nice. And I'm just telling you, the tangent vectors you get from here have a much nicer description than the ones that you get from here. So I'm going to choose this simpler looking parameterization again. So with that choice made, let's compute our tangent vectors to be r sub x will be 1, 0, 0, and r sub z will be 0, 0, 1. Oh my gosh, we just saw these in the previous part, right? So their cross product now is, well, let's do it. In the first component, we get, 0, right? In the second component, we get minus 1. And in the third component, we get 1. Oh, no, sorry. In the third component, we get 0 again. Sorry, I lost my mind. Okay, so notice, though, at this edge of the surface, big S, right, that cross product going minus 1 in the z direction, oh, well, over there on that side, that's pointing inward. So like I was saying in the previous video, that when you have your surface broken into two pieces, you're going to have to make this distinction on each piece. But once you've made it, like once you've determined at one point on each piece which one's pointing inward, that's the choice to make along that whole piece. Okay, so our parameterizations aren't so bad, at least piece by piece, that you would have to choose at more than one point along some piece to determine what's outward pointing. So using the right-hand rule here, it's clear that RZ cross RX is the one that is outward pointing to the whole surface S along S2. Okay, so now that we've got that going on, let's suppose now that we're given some vector field over this whole surface S. So for instance, let's say we have this vector field that is big F of x, y, z is x in the first component minus y in the second component and 2 in the third component. So we're going to compute the surface integral of this vector field over S by adding the two surface integrals over S sub 1 and S sub 2. Okay, and I'm not totally sure if this notation is standard to put the subscript also inside there, but I'm just kind of doing that just to sort out the fact that these are two different things, okay? So, recall for our first surface, S1, we had this parameterization. R1 of xz was x in the first, x squared plus z squared in the second, and z in the third. So now if we evaluate big F along that, well, let's see. Let's go back here. Big F is in the first component, it just is x. So what we'll do is take the function, the x function from R, that is x itself. So I'll say that here is one of these kind of sticky points where it might actually help you to just go back and replace in your parameterization, replace x and z here with really like u and v. Because then you can see that the first one is supposed to be x of uv. And when you read that x off in the formula for big F, it means that function x of uv. So I'm being a little bit quick about this because this video is already long. So if you do have questions about this part that's kind of sticky here, be sure to ask me. But I'll say it does help to just replace these with u and v temporarily so that when you're going back to evaluate f of r, it doesn't feel like you're using x and z to mean two different things at the same time. So what is the x function from the parameterization r? It is literally just x itself. So that's why we put x there. Okay. And so then looking at big F again, the second component of big F is minus y. So then what is the y part of the function y of, say, uv given to us by r? Well, that is x squared plus z squared. So negative y will be negative x squared minus z squared. And then what is the third component of f? That is just the constant value 2. So there is no other thing to put here. So in particular, this guy gets left off, okay? So f of r of xz is given to us by this vector field here. Okay, and now recall over there, our outward pointing normal vectors were given by 2x in the first component, minus 1 in the second, and 2z in the third. So now let's take the dot product of f of r with this cross product here. And so what do we get? 2x squared plus x squared plus z squared plus 4z. So we can simplify this to 3x squared plus z squared plus 4z. And so then the surface integral of the vector field f over the first surface S1 can be computed as the double integral of this function over the unit disk in the xz plane. And this would be a very crucial time now to switch to polar coordinates, now that you actually have to do this integral. So now we'll pay that polar coordinate tax, okay? But before we do that, let's first get the setup going for the second surface integral. Since it should have the same domain at the end of the day, we can kind of streamline and do these all kind of in once at the end. So for the second surface, S sub 2, we had this parameterization, x in the first component, 1 in the second component, and z in the last component. So then again, if we evaluate the vector field f along that, we had the first component function of f was itself just x, which the x function from r is x as well. So we have x in the first component for this composition. And then the second component of f was the function minus y. Well, the y part of r2 is 1. So in that composition, it becomes minus 1. And then the third component of f, again, was just the constant value 2. So we'll put that there. And recall that the outward pointing vectors were those backwards cross product, r sub 2z cross r sub 2x, which if you do out is just the unit vector in the y direction, 0, 1, 0. So now let's take the dot product of f of r2 with this cross product that's unit normal, or this actually is unit normal outward pointing, and we get just 0 minus 1 plus 0, which is just minus 1. Ah, very nice. So then the surface integral of this vector field f over that second part, that disk at the end that kind of caps off the surface, is just the double integral of the function -1 over the unit disk in the xz plane. So there's probably a couple of ways you could do this. You could recognize that it's negative the area of that disk. That would be the most clever way to do it. But since, I don't know, I want to showcase to you how you do this, where you make the sort of, you make the nicer choice to figure out your vectors for your parameterization, and now you have to pay a tax to use polar coordinates to integrate. What do you have to remember to use but the determinant of the Jacobian matrix? So since our region D is the same for both those integrals, we can combine them together and just write that the surface integral over S of the function, of the vector field f is the double integral over the unit disk of this function here, 3x squared plus z squared plus 4z minus 1. So let's switch to polar coordinates. And since I no longer am going to have to refer to the parameterizations r anymore, let's honestly switch to polar coordinates r theta, just because I don't really want to say u and v again anymore. So So we'll translate everything into polar coordinates r theta. So 3x squared becomes 3r squared cosine squared theta. 4z becomes 4r squared sine squared theta. And, z squared becomes r squared sine squared theta, sorry. And then plus 4z becomes plus 4r sine theta. And then minus 1 stays minus 1. And because we're now switching this double integral to an integral over polar coordinates, we need to multiply by the polar coordinate Jacobian determinant, which is r. Okay, so let's see what's going on with that. First thing I think we can do is take inside of here, we have 2r squared cosine squared theta plus another r squared cosine squared theta plus then r squared sine squared theta. So if I yank one of these off the sum here of 3 of them, I can combine it with this one and get rid of use that Pythagorean identity to simplify. So I've done a little bit of a skipping of a step here where we say we have 2r squared cosine squared theta plus r squared cosine squared theta plus r squared sine squared theta, which just becomes r squared in the middle, plus the rest of this nonsense. Now we can multiply through by r, and so we get 2r cubed cosine squared theta plus r cubed plus 4r squared sine theta minus r. Okay. And so now let's do our integral from 0 to 1. This becomes pretty straightforward. We get 1/2 cosine squared theta plus 1/4 coming from that piece, plus 4/3 sine theta coming from this piece, and then minus 1/2 coming from the end. Okay, and now we're going to integrate this function. Let's see, 1/4 minus 1/2 is minus 1/4, so we can simplify that there and integrate this guy from 0 to 2 pi. And so let's watch it go. In the first term, we'll invoke the half angle identity for cosine, which we already have 1/2 outside, so then putting another 1/2 outside from that identity gives us 1/4 times the quantity 1 plus cosine of 2 theta. And after doing that, let's see what we've got. We've got 1/4 plus 1/4 cosine of 2 theta plus 4/3 sine theta minus 1/4. So the 1/4 at the beginning cancels the 1/4 at the end, and we're left with just this expression to integrate. That integral becomes 1/8 times sine of 2 theta minus 4/3 times cosine of theta, which we can evaluate at 0 and 2 pi. And what happens? Well, sine of 4 pi is 0 minus 4/3 cosine of 2 pi. Well, that's just minus 4/3. Okay, and then we will subtract 1/8 sine of 0, that's 0, minus 4/3 cosine of 0, which is also minus 4/3 again. So then we'll have minus 4/3 minus minus 4/3, which becomes 0. So this surface integral in total is 0. So that should leave us wanting to know more. Why was that? So we'll say this story is not over. But this video basically is. So there is something definitely more going on here. And there's a very nice, very clever theorem that will help us see that this integral is 0 by doing much less actual computational work and a little bit more high-minded thinking, which is something we love to be doing in this class and we love to be doing all of the time. But before we can get to all of that high-minded nonsense, we will first have to meet some new terms related to vector fields, get a couple more tools in our toolbox before we can kind of proceed. So stay tuned for that in the next talk.